Okay, so it's a great pleasure to welcome Emmanuel Candès from Stanford University for the NSF Tripods plenary talk. So Emmanuel Candès, he is a faculty in the Department of Mathematics and Statistics at Stanford with a course appointment at the electrical engineering department as well. As you know, I don't know, I think he doesn't need an introduction. He's so well known in the area of signal processing, information theory, computational mathematics. He has done like extraordinary work in compressed sensing and so on, lot of breakthroughs, and he has received equal number of very prestigious awards, starting with Alan T. Waterman, which is and MacArthur Fellowship, which is known as the Genius Grant. Emmanuel is also a member of the National Academy of Sciences and the American Academy of Arts and Sciences. So it's a great pleasure to have him here for our NSF Tripods workshop. So welcome, Emmanuel.
Thank you very much for the kind introduction. Can you hear me? Yeah, okay. It's a real pleasure for me to be here and to address a distinguished audience. So we're doing a lot of things at Stanford, and I decided to focus on a specific project rather than telling you too many stories at once. I'm just going to try to tell you one, which has to do with the importance of selection in modern science and the importance of being able to select well and yet using the most fancy machine learning tools that you can think of. And one of the reasons it gives me great pleasure to give this perhaps more focused talk, it's because I would say that the main driving force behind this project is my extraordinary students named Ying Jin. And I think you should take me as a messenger more than anything else. And also we were fortunate to collaborate with my Stanford colleague, Yuri Leskovich, and also with Genentech on some of the things you'll see. So the motivation for what you'll hear is essentially how can we accelerate drug discovery. So, you have some popular graphs about drug discoveries. And basically what you can infer from these graphs is that it takes more and more money to bring a drug to market, and it takes more and more time. And so it's not surprising that people want to accelerate drug discovery and make this process more efficient. And here we live in the center of biotech and also of AI, I suppose. So I don't need to tell you that it's one of the areas among the many areas of science and technology where AI can bring something really useful. There's an enormous excitement about the potential of AI for accelerating drug discovery. And so you have lots of articles being published about AI is great, it's going to transform the way we bring and discover drugs. The future of biotech, I don't know what your colleagues would think about here, but is AI driven entirely. And so the promise of AI is that we're going to be able to transform the drug discovery process into something that is very low cost and very efficient. Because as you'll see, the promise is that we can substitute costly experiments with just predictions from machine learning models. And so, the importance of reliability is like, okay, we have a lot of compounds that might be interesting as drugs, and we need to see whether these compounds have an interest. And so we're going to try to use AI to do something like this, but it's extremely important to have reliable predictions. And so what we have to ask ourselves is, what if the machine learning models we use give a lot of false leads? And so this will lead to a failure of the promise of AI. And I don't know if you've seen the articles lately, but this is an article published in Nature in October of last year. AI's potential to accelerate drug discovery needs a reality check. I mean, people are slowing down. There's a lot of hype, and now there's a cooling off period. Okay. And so we want to talk a little bit about this space and other problems similar to it. So the thing that we'd like to do is, if I'm going to use AI to actually, test drugs for clinical trials, it's important that I don't make a lot of mistakes, because a clinical trial is expensive. So in this talk, this talk is very general, but again, all of my application will be focused on drug discovery, but of course it can apply to many other things. But in the context of drug discovery, this is what we have. You're sitting at Genentech, for example, and you have a library of compounds, and it's a big library. And you would like to know which compounds are interesting, we should pursue for potential drug development. That's basically the basic question you're facing. And so what I mean by interesting in this talk is going to be that if I could actually go through a very expensive experimental process, I would be able to measure things about this compound, and the outcome Y that would be able to measure would be sufficiently large. So in this lecture, we're going to say that to be interesting means that there's an unobserved response. If I could go out and measure it, that could be potentially very large. Another example of a problem like this is, I don't know, I receive a lot of CVs from applicants, and I would like to select candidates for an interview. And of course, you know, there's if I could actually perform these interviews without performing the interview and knew how people would do on interviews, that would be very good. But of course, interviews, flying in people is expensive, and so on and so forth. So what we're going to talk about in this talk is that there is a quantity that I'm interested in. Here, the quantity that would be going to care about is the affinity of a drug for a certain molecule, a disease. And so, you know, this is something that I could potentially measure in the lab, but it's very expensive. But I would like to follow up on molecules that have a high affinity for a target molecule, because if you have a high affinity for a target molecule, maybe that can influence the development of the disease. And so as a scientist, you ask, well, I have a lot of compounds that are unexplored, and so which drugs look promising? That's basically the question you want to answer. But this is, of course, you know, you could be sitting in HR, you receive a lot of CVs, and which people should I interview? Okay. Because once you, yes.
Couples with the target, you also don't want it to be binding to all sorts of other things.
Right.
Is
so
that
the many objectives you might have, absolutely. So Rob is asking, you know, you need to care about specificity, absolutely. The many objectives you might have. What we see is that, you know, it's useful in this talk to think a little bit about, if I could perform an experiment, what would I end up selecting? And you want to kind of be able to select without performing the experiment. So can I predict the outcome of the experiment and select with confidence? Okay. Because if we could do this, then I could perhaps select a bunch of molecules that then I would test extensively, and these are costly. Maybe I would start clinical trials, they're even more costly, and so on and so forth. Is it clear what we're trying to do? So, of course, the way you do this up till now is that, well, you look at your library and you're going to evaluate, you're going to go in the lab and hire a lot of people to make a lot of measurements, and that costs a lot of money. But I don't need to tell you that, you know, all the articles we saw at the beginning of the lecture says, what about we just bypass this thing? We're going to say whatever, and please use my words, interpret my words a bit loosely. We're going to use AlphaFold instead. All right, or fine-tune AlphaFold-like models, stuff you develop. You know, we're going to use machine learning to bypass the thing. And so this will lead to decisions. So this is an interesting problem so that we can think of it like as this way. So we have a model, pre-trained prediction model, and in this talk we deal with very fancy models like graph neural nets and a lot of very fancy stuff that we actually did not develop, that we're going to end up using. And then you have some covariates X, which are the physical or the chemical features or the amino acid that makes a drug. And you have a response Y, which is a binding affinity. So it can be either discrete, 0, 1, it says whether the drug binds to the target or not, or it could actually measure something a bit more sensitive, which is how well does it binds to the target. So you have this machine learning model. And then, of course, you have a few screen drugs. So drugs for which you have actually is a true label. And so these are what you've seen. And so for these drugs in blue, you have measured the affinity. And of course, you're sitting, and I'm not kidding you, like people have libraries of 2 billion compounds, and they're asking which one of them should I look at next. And so you have a lot of test samples, far outnumbering the number of training samples you have, for which you do not have the affinity. So these are the new drugs. And what you would like to do is your boss has given you some threshold. It says, well, you know, I would like you, Emmanuel, to find in this library YN a lot of drugs for which, if we were to measure the affinity, it would be above these thresholds we gave you. Because this threshold is completely specified by the user, we can see that they are or can be random, which is where the theory is going to become even more interesting. So the goal is to find in these test cases, without measuring the Y that would pass a certain threshold. And this threshold is deemed to be the threshold of interest. And it can be molecule dependent. For example, if you belong, perhaps that's in going in a Rob's direction, if you belong to a class of drug, the threshold might be different than if you belong to a different class of drugs, because they are drugs that are perhaps easier to bring to market than others, and where they have less secondary effects or things like that. Okay, so this can be very highly drug dependent, can also be random. We'll see these examples later. And so this is a user specified threshold that becomes interesting. Okay. So this is what it means to be interesting, is to exceed a user specified threshold. I talk about drug discovery, but you can see that it applies to a lot of things. So for example, Google DeepMind, they added 400,000 new compounds. Well, great. What are you supposed to do with that? Well, you know, you have a thing you want to do. There's a good property you want to have. Which one should you look at first? You know, machine learning, I don't think I need to tell this audience that we use it more and more. So you receive a lot of applicants, and which one should you look at? The why would be what you would learn after an interview. And well, you know, which one should you look at so that you don't waste a lot of HR resources? Customers, you know, I think today companies have access to enormous pools of people. Which one should they go after to recruit as customers? You know, it's expensive to go after people, and if you go through the pain of going after people, you would like them to enroll or to become your customer. And so it's a very similar problem. So this is a problem that pervades a lot of things. So there's a lot, we do prediction because we want to make decisions. And here's the decisions is, which drug am I going to test? Which person I'm going to interview? Which person I'm going to try to enroll as a customer? And there are many, many other examples. Yes?
Threshold that?
No, because maybe, for example, you already know a lot about a class of drugs. You have some drugs in that class that work quite well. Are you really interested in a new drug in that class? Maybe not. So the threshold is going to be high. But then there is this other part of chemical space where you don't have much. And it might be that you become interesting if the threshold is a bit lower.
I see.
Because this is something you have not explored yet.
I see. Yeah, thank you.
Yeah. I wanted to make it general that the threshold can be drug dependent. You know, I know people in this room, I at least have recognized one who is working on causal inference. You know, it could actually be a counterfactual, the threshold. Like it could be yn plus j is what is the outcome, whether if you get the treatment. Cn plus j is what if you got the control instead. And so here's what it's asking is, for which people are you sure that the treatment is beneficial? And then in this case, Cn plus j would be actually random and unit dependent because it's your response to control. So it's important for us to keep it at this level of generality. Okay. So what are the challenges? So we have this kind of fancy machine algorithm, and if you know what they do, then we need to talk because they're so complex, and we use them. We really use them a lot, but you know what they do is they return predictions. And now, you know, the challenge is like, how confident can we be in these predictions? Because they're going to condition downstream experiments, downstream clinical trials. So it's extremely important to understand the reliability of these prediction algorithms, of these graph conditional networks and all of that stuff that we're using, So how can you be confident in these predictions so that you can follow up on them? And so this is where we're going to need to do a lot of uncertainty quantifications in the point prediction returned by this algorithm. And because, I don't know, like I was trained in statistics and things are Gaussian and this and that. I mean, look, I mean, X, my covariate space is like all sequence of amino acids. It's a fold, the response is a shape of a protein. Like, I don't know. We cannot start putting models on this stuff. And also, as I said, I want to be able to work with the latest. So if Rob comes with a new prediction model, he says, Emmanuel, I found this great thing. I want to be able to use it. Says, I don't want to be able to tell Rob, no, it doesn't fit my theory. It's not a linear model. I can't do much. I want to be able. So we're looking at a lot of challenges, and we want to understand the uncertainty, but at the same time, we want to make no assumption, which seems to be a contradiction. Okay. Now, understanding uncertainty in actually drug discovery is not a new thing. And there's this wonderful field, conformal prediction, which is a way of trying to quantify uncertainty. Have people heard about conformal prediction before? Can you raise your hand if you have? Yeah, it's a wonderful field, but you'll see that it is not the answer. That essentially turns point prediction into prediction sets with guarantees that you'd like. So you ask yourself, there's this drug, I observe this X, but not its affinity. Can I predict the Y? And maybe you use your fancy neural net, and it says, well, the affinity should be 14.5. And what conformal predictions does, it transforms this number into a range of predicted affinities with specified coverage probabilities. That is, it's going to contain the true label with a given fraction of the time. And you can do this for continuous response. You can do this for discrete labels. So for example, here yn plus 1 is actually taking value in 1, 2, 3. And then the algorithm would say, I think it's a 2. And then what prediction inference would do is that it would transform these 2 into a prediction set. And these prediction sets have a wonderful property. And this is really a field that was pioneered by Vladimir Vogt, who is a little bit of a hero of mine, I should say. And what we've learned over the last 20 years, and we've learned how to do this better and better, is to return prediction intervals that contain the true label 95% of the time, or 90% of the time. So it's very cool because you can use a prediction of a machine learning algorithm and sort of transform this into a range so that your range contains a true label a given fraction of the time. So that's pretty cool. And I don't know, most of you go to NeurIPS, I would say a very healthy fraction of papers at NeurIPS are actually about this subject, which is great. Okay, so here are the challenges. So what the challenges are is that, okay, I have my first test sample, my second test sample, and for each of them, I can construct a predicted range for the affinity using, again, the most fancy machine algorithm that you can find. And so what we know from conformal prediction is that when I examine a large library of compounds, 90% or 95% of them, that's up to you, will actually contain their true label. So we have a form of uncertainty quantification. And this theory and this construction from Vladimir Vogt and so on, and we've worked on this enormously, of course, at Stanford, said that, well, 90% of these intervals will actually contain the true label that you can't see. But that's not what happens in reality. What happens is I'm going to do something like this. So let's look at them. And this one look very interesting to me. Why? Because the predicted range for Y is high and short. So I'm pretty sure that Y is above a value somewhere. So how about I go and test these guys? And now for people who know a little bit of statistics, we're doing something which is quite dangerous because now it's after looking at all the data, we're going to select. And then the question is, are the properties of inference holding over the selected? So can I actually use conformal prediction to actually create intervals when I see some sweet intervals that are high and short? It says, well, that's an indication that is an interesting drug. Should I go and select them? And that's what everybody does. So people in drug discovery, they are actually aware of classical conformal prediction, and they're sort of using it, except they're using it to do selection. And in marketing, it's the same. And in disease diagnostic, it's the same. So everybody is using this sort of uncertified method, but they forget one thing. And they forget this, which is in practice, okay, we got that we need to take care of uncertainty, so we're going to construct prediction intervals. Then I'm going to look at the result, and I'm going to select interesting stuff. And what I'm saying is, what sort of everybody is an intuition for, is that this is going to lead to a very, very, very strong selection bias. So to give you a sense of the selection bias, here is actually a real data experiment. So this is actually on a real drug discovery data set. So I set miscoverage level to be alpha. So if alpha is 5%, it means that 95% of my confidence interval should cover the true label. And so on the x-axis, you see the target miscoverage, which let's say is a parameter that I can freely vary. And on the y-axis, you see the realized mixed coverage. And you see how the theory of Vladimir Vogt works. It's perfect. That is, you want 10% miscoverage, you get 10%. You want 30%, you get 30%. These marginal intervals that we construct have exactly the advertised property. And so what this shows is that conformal prediction works. It does on real data set what it's supposed to do. But that's not what people do. People say, I'm going to select prediction intervals to the right of the threshold my boss gave me, because that's what looks, it says it predicts with a lot of confidence that Y is above the threshold that Rob gave me. And now if I do this, this is the error rate. You want 1% error rate, you got 40% error rate. You want 10% error, you got 90% error rate. Right? This is something that we all know in statistics. So it's you want 1%, you got an enormous error rate after selection. So you're going to waste a lot of resources. And this is, of course, the winner's curse, is that the winner is just too good to be true. And so this is a problem that has been recognized in statistical science for a long time. And I think the earliest reference I could find was research in 1989, which inspired a lot of research and the birth of a field called selective inference. But basically, what we need to pay attention is that there's a lot of things at play here, right? There's no model. We want to use fancy algorithm, and then we're doing selection on top of it. Okay. So our proposal is to be able to, in fact, we can be a bit more fluid than this, but let's say that just to fix ideas, our proposal is to say, okay, I have my machine learning algorithms. Can I discover drugs among these 2 billion compounds for which the outcomes exceed the threshold, but the fraction of false positives is under control? And so what is for me the fraction of false positives is the number of discoveries. So R is going to be my discovery set. This is my recommendation. We should go and test or develop these molecules for which after measurements, they would not do what they were supposed to do. So they're not interesting over the set of discoveries. So it's saying that if we follow this principle, if we somehow can find a rule that would select interesting drugs where the false discovery rate is below 10%, it means that we're not going to waste more than 10% of our time in follow-up studies. We can set it to 50%. Of course, we're going to discover more, but we control the fraction of the time we spend following uninteresting leads. Okay, so if I control the false discovery rate, then it says that most AI-powered decisions are correct and that your resource allocation is efficient. So the question is, how are we going to do this? So what we're suggesting is that we still want to use machine learning models, but we're building around the ecosystem of machine learning. We're going to add what are protection layers. You can think of conformal prediction as a protection layer, but it's not good for what we want to do because it does not address the selection bias. And so we're going to construct a protection layer such that when you mix your black box with your candidate pool, you come up with interesting molecules, and you know that 90% in your pool or 80%, whatever your false discovery rate you set it to be, will be actually of interest to you. Okay, so we're going to see how we can do this, and so this is a paper that was published with Ying in the Journal of Machine Learning Research last year. I should say that it was very pleasant to submit this paper because I think it's probably the first time it occurred to me, like people said, just don't change it, put it there. It's very, very unusual that, okay. So what are we going to do? We're going to try to test, and it's not classical what we're doing because we're testing random hypotheses. These are not hypotheses about parameters of a population. There is an outcome yn plus j. This could be actually random, and we ask, can you please compare the two outcomes with making very few mistakes? Okay, so that's what we need to do. And we're going to do this in two steps. First, we're going to try to construct calibrated confidence measures, which we're going to call conformal p-values. And then we're going to try to sift through them to see what looks interesting and what doesn't look interesting to control the false discovery rate. Okay, so, all right, so we have our machine algorithm, and let's say it returns a point prediction about the affinity. And so with this machine prediction, we're going to construct what I'm going to call from now on a conformity score. And the conformity score is this. For example, it has to be monotone in the response. So if I give you the same value of x and y increases, then the conformity score has to increase. So that's the definition of a monotone conformity score. So it has to have this property. And an example of a conformity score would be the residual, but the sign residual, that is the difference between the response, the affinity, and the predicted affinity. It can be something a bit more fancy. It can be the difference between the affinity and the predicted affinity over what you think is sort of the accuracy of your prediction in this part of chemical space. Or we can be even more fancy. We could say, V of xy is what is this? It's a conditional CDF of y given x. Like it's an estimate, and you can ask your neural net to estimate such thing. So what in more is like it's a measure of model misfit, and what I want it to be is it has to be monotone in y. Okay. So now I have some test training samples, and so I can compute these scores on the training sample, and I get a histogram. Let's say they look like this. And then I want to compute test scores, but for test scores, I don't have the y, so I'm going to impute the threshold instead of the y. So I'm going to compute test scores, which have exactly the same formula, but instead of the y, which I cannot see, I'm going to impute the threshold instead. And I think what we're going to try to do essentially is to compare how big is this with the imputed threshold with respect to the distribution of what I saw on the training set. Okay. And now what we do is to compare this is like we can construct a measure of confidence. And do people know what p-values are? Most people should know. It means it's a tripod about data science. So I think we know, right? Okay. I know p-values have a bad rep, but come on, I mean, okay, so it's an important concept. So the p-value is going to just measure the rank of this imputed test score compared to the rank of the v. So the p-value is going to be very small, for example. It's going to be very, very small if there is no vi below this. So if vi is over here, you're going to have a very small p-value, and if vi is over here, you're going to have a very high p-value. And so these are p-values there. So I'm comparing the prediction at the threshold passed through this test scores with what I observed on the training sample. Okay. And so basically, I'm ranking the v hat, the test samples, with a value of y, which is the threshold, against the training score that I got. So these are the blue I've measured, red I haven't measured. and I'm just comparing these scores. Okay, so you see I make no assumption of any kind, nothing. Okay, so, you know, if we were to do a little bit of unpacking, this is just for people who are interested in this sort of things. There's this p-value has an interpretation, and its interpretation, which is that, you know, I'm looking at drug J, the test sample J, and I'm constructing a prediction interval. It's not a confidence interval because it's trying to predict the label. And then I'm going to try to enlarge this prediction interval until it reaches a threshold. And the confidence level at which it reaches the threshold is actually the p-value. It's an equivalent formulation of what I've just like. Enlarge your prediction until you touch the threshold. And that level, you define your p-value. This is your p-value. It's an alternative definition, but I'm gonna use this thing. But it has a very clear interpretation. The smallest confidence level, the smallest confidence level at which you include the threshold. It's to break ties. It's just to break ties.
Every J has a different independent
U. It's to break ties, and this is going to make stuff uniform.
Gotcha.
Just to break ties. We can remove it. It doesn't matter because you can see that the uj over n+1.
Sure.
It's just to break ties.
Thanks.
Yeah. Okay. Thank you. Okay, so now we have p-values, and now we're going to say, well, you know, I'll use my machine learning algorithm. I have 2 billion compounds, and therefore I have 2 billion p-values, and which are going to select. We're going to use a procedure that is extremely popular, which is called the Benjamin-Hochberg procedure, to actually select promising thing among these 2 billion things. And the way it works, people are familiar with Benjamin-Hochberg? No? Okay. It's a very important technique. I don't need to convince you that it's important. I looked at Google Scholar not long ago. It's a paper with 102,000 citations. You know how many citations there were to the FDR paper like last year? 14,000. So if we look at this paper, like this will be like 116,000 next year, 100. Okay. So it's a procedure, and we are going to use this procedure to actually select promising things. And so basically what this procedure does, if people don't know about it, I can explain it quickly. It's just like you're going to try to find an adaptive threshold that depends on what you see, and you're going to select all the molecules whose p-value are below this adaptive threshold. Okay, that's what it's going to do. Okay. And so the kind of the surprising result, I find it surprising, is this, that if you apply this procedure, you compute p-values the way I said you compute them, and you apply Benjamin-Hochberg, then that controls the false discovery. That you guarantee that in the list I give you, whatever threshold we decide, the fraction of false positives is under control. And the reason I'm excited about these results is that there is basically no assumption. None. So there's no model, no Gaussianity, no linear model. You can use your favorite algorithm. And so as I hope you see is like there's this world of machine learning, and you do what you can do, and then you're building this world that wraps around it so that you can actually trust the decisions that you're going to make. And so this is true for random Cn plus j. So for example, this is a framework that is flexible enough to answer a question like this, where Cn plus j can be random. So if we think away from molecules, we could say, for whose health risk on the second day will be higher than upon admission, which patients are better off under treatment, you can answer questions like this. And it's more general than I care to write. So it's a very fair general statement that shows you that you can control the false discovery. And so it works for arbitrary prediction model, data distribution, random threshold, dependent data points, a lot of stuff. So okay. All right. So so basically what we're going to do is that what the procedure does, it ranks the test sample by the value of the conformity score evaluated at this threshold. And then it's going to calibrate these ranks to select ones that look interesting such that the proportion of false discovery or false positive is controlled. And so an example is if you look at the residual, the signed residual, where this is a true affinity minus a predicted affinity, then why is it that this procedure makes sense? It makes sense because if you observe that this number is small, and what does it mean to be small? It means that it's small compared to stuff you saw on the training set. Okay, so you're in the left tail of these numbers. So remember my histogram, you're on the left side. So you tend to be small. How small? Well, I'm going to compare you with sort of these guys. And if you're small, it means that, well, Cn plus j minus mu hat is small. This is your predicted affinity. This is small. So presumably, the real affinity is higher than Cn plus j. And so the selection makes a lot of sense. So we have reason to believe that Yn plus j is above Cn plus j. And then you say, well, but that's all wishful thinking. And that's why we're going to calculate this dependence threshold. And we're going to use the Benjamin-Hochberg procedure to do this. How small do you have to be for me to believe that you actually, when I'm going to measure you, I'm going to find stuff that I like and not stuff, I have to justify what the employees do. Well, this is what the BH procedure does. Okay. Okay, so why is it that it's working? So this is just for people who care about stuff like that. Is that the remarkable thing about the construction of these p-values is that they are calibrated in the sense that they are actually uniform. That is, if indeed it is a case that Yn plus j is below Cn plus j, then the chance that your p-value is above t is below. So like a uniform is the right comparison. So they're valid p-values. But, and this is why this result is very hard to establish, or at least why I need geniuses like Ying to actually work on this. It's because the p-values, for those of you who know a little bit about Benjamin-Hochberg, they're not independent at all. And this is extremely important what I'm saying, because the p-values that we calculate are all very dependent, actually. Why? Because they all depend on these guys, on what you observed on the training set. So these p-values, they are not independent. So you cannot just open a textbook and say, oh, yeah. No, they are not. And so you're going to have to deal with that. And so there's it's not a small feat. They are well calibrated marginally, but they're not independent. But what we showed is that they have a property which is remarkable, that they're sort of positively correlated. And when things are positively correlated, Benjamin and Hochberg are happy. And so it's good for the Benjamin-Hochberg procedure. So they are not independent, but they're positively correlated. And that lets you go through. But this is really where there's a lot of technical contribution. A lot. So how to choose a score? So this is a bit like, how do you choose your learning algorithm? How do you going to extract information from your learning algorithm? It's a bit like, how do you choose a test statistic? And we have a lot of choices. And if you look at the paper, we say, you can do better than looking at residuals and so on. And maybe I'll skip that. There is really like, now you're going to play a game to kind of boost your power, try to discover as many things as possible. And to boost your power, you can say, well, how should I design this V? And we have lots of ideas on how to do this. I'm not going to discuss this because I'm going to run out of time if I do. But in the paper, we show a lot of possible choices of V so that we can boost power. Okay. So here's the real data set. We want to find active drugs for HIV with FDR control. So here we're cheating because I want to show you grand truths. So in fact, there's a lot of drugs for which I know the grand truths, but I'm going to pretend I've never seen them, and I'm going to try to make predictions. So we have a Y, which is either the drug interacts with the disease or it doesn't. And then we have 41,000 cases in total, and I'm going to do a 6-2-2 split. So I'm going to fit a prediction model, then calibrate it on 2, and then on the last thing, I'm going to show you how we do. Now, this is a very unbalanced data set. Most drugs don't bind to this thing, as you can imagine. And we want to select subsets with 90 or 80 or 50% of active drugs. And this is like, I don't know, it's like too good. For me, it's too good to be true. So this is actually real data, real drugs, real graph convolutional graph networks, and so on. And so what we see is we see the realized FDR. And so you want 0.1, you get 0.1, you want you don't get like 0.5, you get 0.1. Like, so this is a target, and this is what you get. And of course, this is what you do if you don't do what I'm saying. Like you just trustly blind, like the marginal, you don't take into account the selection bias. And then you are in huge trouble because like most of your things don't pan out. And so someone following this protocol would get a huge lead because, you know, to get the first interesting thing, you're gonna have to look at 20 uninteresting things first. And this thing, you'll get it immediately. Okay. And then you see, of course, as the false discovery rate increases, you see the power, which is a fraction of molecules that pass the threshold. And of course, you know, there's a trade-off between false discovery rate and power. And so as I'm relaxing the fraction of false positives, then I discover more and more interesting things. Okay. So here's another data set. It's a Davis data set. So now Y is continuous. Now instead of being binary, X is a feature for drug target pairs. There are 30,000 drugs, same thing. And now the coefficients are going to be random, the threshold. They're going to be basically quantiles of the affinities for training pair in the same drug. So there is my training set, and Cn plus J, let's say I'm class A, and I'm going to look at, well, what is the 90th percentile of the Y for class A? And that's my threshold, because I need to be above that. And maybe for class C is like the 80th percentile. And so now I'm going to, okay, so now it's random, because it depends on what I've seen. And you see all these methods. So let's look at the red. You know, you want 10%, you get 10%, you get 20%, you want 20%, you want 50%, you get 50%. And of course, as you relax the FDR level, then this is quite remarkable here, is that you discover half of the drug in your library are going to be found by this procedure. And the only price you're going to pay for this is that you're going to waste 50% of your time, but you're going to discover over half of the drugs that do something interesting. Okay. Now, we, of course, working with these partners, as I mentioned. And so it's just to give you an idea of, you know, we use these neural encoders, these embeddings, these graph convolution networks, these CNNs, stuff that have been designed exclusively for drug discovery. And then we have a lot of different data sets. And so this is all real data. And you see, like on the x-axis, a kind of fraction of false positive we want to control. On the y-axis, we see the effective false discovery rate we get, and it's smack on the 45-degree line. These are very boring plots. I don't think I could even apply to Stanford with plots like this. But for me, they're very important in that you are doing exactly what you said you would be doing. I hope it's not true, because Ying is on the job market. So, okay, so we got what we want. Now, the last thing I want to discuss in the last 10 minutes is one thing that people discuss all the time in machine learning these days, is that what the theory you've seen assumes is that the test sample look like the training sample. But in reality, that's not going to be the case. And so we're going to deal with distribution shifts. And so distribution shift in all the application we look at, which we have ignored so far, is actually very important, because the theory you've seen and the method you've seen work if the drugs I'm asking you to evaluate are sort of representative of the drug you have in your training sample. But that's not what's going to happen in real life. In real life, the drug for which I have a Y, they're not representative of the drugs for which I do not have a Y, because they have a Y because they were thought to be interesting in the first place. So there's going to be a shift between the training drugs and the new drugs. They're not the same. And I'm going to prove to you that they're not the same. Okay, so no, because you prefer drug with, okay, so this is what we just said. So we have not dealt with this, and it's about time that we deal with this problem. Okay. And of course, it's the same issue in everything. When I do job hiring, you know, the people for which I have a Y, they are the people I perhaps hired, so they're not representative. The students Stanford admitted, well, they were admitted for a reason, right? So we have this shift. Okay, so now we're going to assume, and I think it's a reasonable assumption in all the applications we work on, that there's a covariate shift between the two populations. And what that means is that if I were to look at the ratio of the likelihoods, which I have no idea what they are, between the training and the test samples, so Q is test and P is training, I'm going to assume that the difference in distribution is only because of X, not in the condition of Y given X. And I think it makes sense, because the conditional distribution, like the shape of a protein given its sequence of amino acids, what does this have to do, whether it's in the training or not in the training set? Right? So it's only depending, but what distribution of amino acids do I have in the training set and test set? This can be quite different. Okay. So we're going to assume that we have a covariate shift, which is something which is frequently discussed in the field. And this makes sense. And I still want to do the same thing. So I still want to find samples that exceed some thresholds. Now, what we're going to do when we're going to construct the evidence for being interesting is what we're going to do is, if I use this covariate shift, there are some test samples that the training samples that I'm going to upweight and some that I'm going to downweight. So when I'm actually looking at my comparisons, whether the training sample is less than the test sample value or the predicted test sample value, is going to be something like this. It's going to be multiplied by a weight. And if the training sample is not very likely under the test in the test data set, then it's going to receive a smaller weight. If it's more likely, it's going to receive a more likely. Right? So this is what I'm trying to represent here, is like, you know, the test sample and the training samples are quite different. And I'm just not going to calculate just the rank of En plus J amongst what I've seen, but among something that has been weighted in such a way that the training sample starts to look like the test sample. Okay, that's the only modification. Yes.
So, I mean, I mean, all the samples you have in the training data are maybe selected using some information about like how drugs bind, blah, blah, blah. So I don't think that the likelihood should not depend on Y, because probably whoever selected the drugs they really wanted to evaluate had some knowledge about, okay, this is actually likely to bind them.
So you're thinking that this is not true?
Yeah, like maybe I didn't follow your reasoning.
Well, suppose we're looking at a physical property, right? And so let's say Y is the shape of a protein. If it has a certain, if its shape is in a certain category, it binds. If it is not, it doesn't bind. And the shape is going to be determined by the sequence of amino acids. Do we agree on that?
Yeah.
So the distribution of Y given X cannot care about whether you're in the training or test sample. It's just the shape is a function of X. No matter where X is, that the conditional distribution doesn't change.
Oh.
What changes though is you in the lab, which X's do you want to look at? So for example, you look at the literature and you say, these drugs have been found to do this, these drugs of this type. That's where you're going to look at. I think if we put a lot of covariates, it's going to become true. I mean, at least I'll try to show you through pictures that it's actually a true assumption. But thank you for the thing. Okay. So now we're going to compute these p-values. And these p-values, they are still good in the sense that there are still honest measures of scientific evidence. Nothing has changed. What has changed, though, is that I cannot apply Benjamin-Hochberg because they don't have this form of positive dependence that I talked to you about. And so that I cannot do anymore. I cannot do Benjamin-Hochberg. So now the selection procedure, which I will not discuss, has to be more involved. And it needs to be more involved. And we have actually examples where if you apply Benjamin-Hochberg under covariate shift, you're going to inflate the false discovery. And so we have a fix. And the fix I won't discuss. But basically, what the important message here is that each molecule will have its own threshold. Instead of being smaller than a common threshold, it's going to have its own threshold. Okay. Okay, so here's an example. It's a data set we've already seen where we are trying to predict continuous binding affinities. It's a data set we've seen. Cn plus J is random again. It's a 80th percentile of affinities for training pairs with the same binding target as J. So it's a random threshold. But here you see the histogram of the test scores, and here you see the histogram of the training score. So you see the training is shifted to the right. Right, because that's what we did. We constructed the training set so that it's different from the test set. It tends to have test scores that are higher. Okay, but when we apply this strategy with the selection strategy that I've now talked to you about, nothing changes. You want 50%, you get 50%. You want 25%, you get 25%, and you want 10%. And of course, this is again my real data set. And so it doesn't change. And so by showing you it's a proof, a data science proof of a covariate shift, which is that if I apply the method without dealing with a covariate shift, I would get this false discovery proportion. So this is, again, a real data set on small molecule data set. So, and so the training set and test sets, we constructed them with distinct scaffolds. So structural property, and the covariates are learned representations of molecules. And so if I don't apply this kind of reweighting that we saw, I'm going to get the false discovery proportion, which is way out of line. Too many false discoveries. And I want to say that's a proof that there's a covariate shift, that there's a distribution shift. Otherwise, we know from theory it should be on the line. And then the blue curve is the false discovery proportion with these weights, and we can see that it tracks. Of course, this is a smaller data set, so this is not the false discovery. The false discovery is in expected values. This is just the value of the random variable itself. In each experiment, what false discovery proportion did we get? And so we see this, and we see that it tracks it. We also have, well, okay. So the method is flexible enough to actually deal with covariate shifts, and so that we can get the FDR control. And so we show a form of robustness to distribution shifts. Now I just wanted to, in the last minute, I just want to say you can do other things with this. I'm not going to discuss this, but you can do other things with this. Something I'm interested in is, you know, there's in causal inference, there's this thing that people call the individual treatment effect. So, you know, I guess most people are familiar with causal, at least the basics of causal inference. But, you know, YI would be the response of Emmanuel to treatment, and YI0 would be the response of Emmanuel to placebo. And of course, I cannot observe both, because either I take the placebo or I take the treatment, but not both. Still, there's a quantity delta I that people care about, which is YI minus Y. So what's the difference in health outcome between the treatment for me? Not for Rob, for me. Okay. And so what you can think of this is like, you know, this could be your unknown, this could be your Y, and this could be your Cn plus J. And so then if you think about our framework in this thing, is that what I would like to do is I have a treatment, but it's expensive. I don't want to waste it. And so what I would like to know is I would like to find individuals, and I have lots of covariates about patients, and I would like to find individuals with positive ITs. So you have a resource, you want to allocate your resource, but you don't want to waste 50% of your resource or 80% of something. So you want to find individuals with positive IDs, people who actually benefit from the treatment. Okay, and so you can think about the test data as the response under treatment, the training data under control, and then testing whether Y input is input is whether the treatment effect is positive for you. And now we can use machine learning and all of that to actually go and try to find patients. And we know that when we allocate the thing, or our loan or our treatment, we're not wasting a significant fraction of resources. And we do this using machine learning on an individual basis. Okay, we actually applied this to real data, but I think I have 5 minutes left, so I should save 5 minutes for question and thank you for your interest and time.
Right. Anybody have a question?
Knowing your weighted conformal prediction, if you don't know the test distribution Q, how do you estimate the weights W?
Yeah, we're going to have to do some things. And so I could be, yeah, so you're asking the thing that, like, we don't know this typically. So we're going to have to estimate it. And then I can talk to you about doubly robustness and stuff, but I don't think it's useful. We do our best. And so what I can show you is exact FDR control if I know W. In practice, when we estimate W, we achieve FDR control. Can I prove it? No. Do I see FDR control? Yes. So for example, here we did our best to actually estimate this covariate shift. And it's not that I actually control FDR, I get it exactly to where I want. And this is, we fit typically exponential tilted models like Q over, exactly. I mean, yeah. So we try to be, and then we hope for the best. So it's a very good point you're making. There's a gap in what I'm doing, which is that in practice, I don't know W. Sometimes you do, because sometimes when you're in a lab, you can say, am I going to look at this molecule? And you might actually have in your hand the decision mechanism.
Thank you.
Yeah. So I have a question about, I guess, conformal prediction itself, right? Which is, if in a situation where point estimate is expensive to get, right? Like, for example, if you're using AlphaFold simulation, it might be expensive to get even a point estimate.
Really?
Maybe, I don't know. I mean, okay, so
training is expensive, but
right.
But forecasting is once the model is trained.
Yeah. So I guess the question is, how much more expensive is it to get a confidence interval as compared to a point estimate?
A confidence interval, you get you want so tell me what you want, because maybe I did not understand.
Oh, yeah. So if I have a model that just gives me point estimates,
yes,
and let's say each one of them costs $1,
right?
How many dollars do I need to spend to get these intervals using conformal prediction, approximate?
Not a lot.
Sorry?
$200.
Okay.
You need a calibration set,
Mhm.
and you need to understand the distribution of your errors. That's it.
Okay. So if the X lives in a high dimensional space or something, it's going to be hard or not
a
hard?
problem.
Okay.
Not a problem. So getting the prediction interval from you, I'm not asking you to retrain, ever. I mean, there are different flavor of conformal prediction, but in the most computationally friendly, I take your model and I don't ask you to retrain it. Okay. And so in that case, all I'm going to do is I'm going to look at the distribution of errors on a calibration set. And that's the thing I'm going to use to actually, that's the thing that is used to actually construct this. So you're looking at the distribution of errors on the calibration set. And then what you do with these errors, you're going to take quantize, stuff like that. But no retraining.
One last question, and we end. Just a quick question.
So early in the talk, you mentioned the marginal guarantee of conformal prediction, and then you said that due to the selection bias, it will corrupt. But then my question is that, like, there are so many works trying to making the conformal prediction to be more conditional. Then aren't those a solution to that problem that you mentioned?
Yes, if we knew how to make conformal prediction extremely accurate conditionally, that would solve a lot of problems, but we don't know that. I'm dealing with a chemical space which is in millions of dimensions. So that's a problem.
Okay. So let's take other questions offline, but let's thank Emmanuel again for a great talk.